Hi all, I would like to thank everybody for the constructive feedback that was left in the previous video. I feel that it got a good response, so I thought I shall continue this style of content, arranging it into a broader series of episodes on this topic. In the last video, I discussed the iconic sounds of old electric trains through the suspended drive method. Often accompanying this sound is the equally as distinct and interesting sound which is often dubbed the camshaft traction system, known for its mechanical noises. In today's video, I will be discussing the history of this system, its beginnings, its peak, and its eventual decline and obsolescence. To start off, we have to go back to the late 19th century when electric trains and tramcars were emerging across Europe and the United States. Due to the significant inefficiencies and marginal capacity of the individual power sources such as acid batteries at the time, electric railways tended to use a static grid system of powered rail or overhead catenary, which operated at a constant supply feed, which was suitable for the continuous operation of the DC motors used by the vehicles on these lines. This presented a problem as the power supply by these systems was too much for the vehicles they powered and would need to be controlled separately per vehicle. Initially for DC systems, current was regulated with the introduction of a bank of large resistors in the circuit between the traction motors and the power supply breaker. As the speed increased and the current subsequently drops in the motors, these resistors would be removed by the driver manually through the individual notches on their traction control handle. This system was impractical, primarily because it was a distraction to the driver to need to remember to remove the resistance if they wanted the vehicle to operate faster, but also because it was possible for the driver to release the resistance too early, overloading the motors. Enter Franklin Sprague, ex-officer in the United States Navy, responsible for assisting in the development of the trolley pole, regenerative braking, and the suspended drive system as discussed in the last video, and now an alternative to the current manual method of traction control. During the development of the Paris Metro Sprague-Thomson sets up to 1908, while Sprague was working with Elihu Thomson to develop the electrical systems, he was alarmed by the thought that Thomson would try to re-implement the simple method of manual power control used in the Paris Metro M1 units, which directly led to the Paris Metro fire of the 10th of August 1903 that claimed the lives of 84 people. Sprague could instead use a notching relay that would automatically close the contactors to bypass the resistors if the current being supplied to the traction motors was less than the threshold within the current limiting valve, preventing the motors from overloading. In order to control the direction of the acceleration, a pneumatic reverser cylinder was used that would change the direction of the current in the armatures of the traction motor. This system was rolled out to general success as the operator would no longer need to worry about notching up the traction controller due to the system to control it being automated. It also allowed for a smoother ride and optimum acceleration as the power generally remained within a band until the motor circuit reached its maximum voltage. In 1927, Leon Heidemann, Director General of the Humont Electrical Institute, designed a variation of this system, which would use a camshaft controlled by an electric servo motor that would control a platted disc that would allow for the notching of the current at different rates and thresholds for each notch, allowing for an even greater control of resistance and consequently the acceleration of the train. It would also allow for the resistance to change from being connected in a series circuit to a parallel circuit, which halves the amount of energy lost due to resistance, allowing for greater current to be accessible to the traction motor. However, even though the motors would have hit their maximum voltage by the end of this point, they were still only operating in a full field. This means that the electromagnetic field is still at full strength and the current will continue to decrease as the motor RPM continues to increase, generating back electromagnetic force. This means that the motors are counteracting themselves at higher speed. However, by bypassing the field current, the electromagnetic field is weakened and subsequently more current enters the armature, meaning even more power as the traction motor can output at a constant rate. This technique is known as weak field control and was tested as early as 1928 for the BR-475 trains in use on the Berlin S-Bahn at the time. The system could also be used for rheostatic braking, by simply reversing the current in the armature and using the motors as generators, where the energy can be returned back to the overhead lines using an excitation device, or simply dissipated through the resistors as thermal energy to save wear on the friction brakes. Resistance control had remained the main method of supply control for DC networks for more than 60 years until the advent of the thyristor, which started to be used on railway vehicles in the 1970s. The thyristor had major implications over the camshaft method as it allowed for continuous voltage control, reduced loss, greater regenerative braking and contactless circuits. The main control method for DC motored vehicles is chopper control. As the title suggests, they chop current by repeatedly turning the current on and off. The timed control of the ratio of the current being on and the current being off is known as pulse width modulation or PWM. The thyristors themselves perform the high-speed contactless switching and are capable of giving a continuously changing voltage, which means that adhesion control is excellent as it can be very quickly adapted to the conditions of the tracks. It also allowed for much smoother operation as the power could be induced gradually and could also be decreased, which was not previously possible in camshaft-based systems. Most importantly, however, it negated the thermal problems that were present in camshaft-based vehicles. Due to the large amounts of current being dissipated into the resistor banks, the resistors could catch fire and become damaged, infamously such as on the NSW Series 1 V-sets, where this was a frequent occurrence due to the hot climate and subpar maintenance. Due to the cost of semiconductor technology early on, particularly in Japan, it would be integrated into the traditional resistor-based circuits, a technique which would become known as field addition excitation control, as it meant that the driver could control the power with more ease at higher speeds than previous weak field control, as well as allowing for much smoother regenerative braking control. Into the 80s, many DC tractioned electric railway vehicles were starting to adopt thyristor PWM control, as in Britain with the Class 317, 318 and 319, and in France with the Rare Z5600 series. As semiconductor technology got cheaper, there was an increase in adoption of full chopper control, which coincided with an increase in the number of trains adopting AC motors, powered by variable voltage, variable frequency drives. Collectively, this resulted in a significant decrease in the amount of trains integrating camshaft resistance control throughout the 90s. These days, camshaft controlled trains are rather rare, considering that they are only found on trains with DC traction motors. But to this day, you can still find trains that are still being manufactured with a camshaft resistor control system. Some examples of this include the ED4 and EP2D, produced by the Demikovsky engineering plant in Russia, in use with the RZD, Russia's state railway operator. Thanks for watching. I hope you have enjoyed the video. If you think I've left some details wrong, please feel free to let me know in the comments and I will correct them in the description or in a pinned comment. I'd be happy to hear if you have any feedback, and if you do, please let me know in a comment below the video. I would like to thank you once again for your feedback on the previous video. I hope it reflected in this video. Until next time, I hope you've learnt something new about the sound of old trains.